Hey guys, welcome to section 2.5. Again, we did jump over 2.4 because it just contains some things that sort of lead into this, but they're not really required material. And so we're kind of free to jump into this next section. 2.5 kicks off the main idea for the rest of this chapter as well as chapter 3. So this is something we're going to be spending quite a bit of time on, and that's the idea of proofs. Proofs are when we take geometry reasoning and we prove something to be true. So the way that these things will start always is you are going to be given some type of information. We call it the given. And then they're going to tell you, use this given information to prove something else, right? And so our goal is to take the steps where we start with the given information, and then we use some geometry reasons like these to then prove whatever it is they're wanting us to prove. And so the way this starts out with this section and the next section both start with some simpler ways of doing that, so that when we get to our two-column proofs, which is ultimately where we're headed, we're able to get through those a little easier and understand them a little better with what we're doing in these next couple sections. So pay super close attention to the ideas that we're going through in this, because these will be around for the next chapter and a half as we start working mostly on proofs. So the way this one starts out is they're going to start giving us some of those geometric ideas called postulates, which are just statements that are accepted to be true. And we're going to be using those and working with those as we go through a couple things in this lesson. So we're going to go through these ideas, but I'm going to show you, these are from the notes. And if you have these notes printed, then awesome, because you already have these in front of you. If not, you need to be able to look at the book and write these down, because these are ideas that you're going to need to know as you go through these examples moving forward. So I want to show you these from the book, though, because they come with pictures that help make these make a lot more sense. And so let me show you these same 7 postulates from your book. And so this is on page 127. So you have access to these on page 127. So let's go through these things really quick. So these postulates, again, are just geometry statements that are accepted to be true. But I love this because they come with diagrams. In fact, if I was taking notes on this, I would draw a diagram to go with each one. So as I look at the first one, it says, through any 2 points, there is exactly one line. And that's not a new idea for us. That was something from chapter 1. A lot of these are from chapter 1. But we're now using them to do other things. So through any 2 points, there is one line. So if I have 2 points anywhere, I know that I could draw a line through those 2 points. All right, that's all that one is saying. Through any 3 non-collinear points, so that means 3 points that are not in a line, there is a plane. So if you look at this, I have points A, B, and C. You can see they're not in a line, they're non-collinear. But there is a plane, this blue surface, a 2-dimensional surface that can be drawn through those 3 points, right? And so we have plane K, right? That's the name of it, drawn through those 3 points. A line contains at least 2 points. So if I ever have a line drawn, I know that there are at least 2 points on that line, right? At least 2. So you can never have a line with only 1 point on it. A plane consists of at least 3 non-collinear points. And that's kind of the opposite of what this one said. So this one said if I have 3 non-collinear points, there has to be a plane. This one says if you have a plane, there's got to be at least 3 non-collinear points on it. So really the same idea. It's just kind of, they're saying it backwards. So we're starting with one idea and ending with the other. If 2 points lie in a plane, then the entire line containing those points lies in that plane. So if I have 2 points, points A and B, and they are in plane K, all this is saying is that if those 2 points are in plane K, well then the line that I draw through them has to also be in plane K. So again, if we know that 2 points are in a plane, we know that the line that we draw through those 2 points are also in that plane. If we go down to the last two here, so again, these are all from chapter 1. So if two lines intersect, you can see that if two lines intersect, then their intersection is a point, right? We would call this the point of intersection. So if they ever say something about identifying the place where two lines intersect, we know we would be identifying a point. However, if two planes intersect, so you can see plane F is the blue one, plane G is the green one, and where those two planes intersect, their intersection is a line, right? And so line W is the line of intersection between those two planes. So hang on to that idea, super important postulates. We're going to use some of those right now as we go through a few examples. So let me go back to this. So what they're wanting us to do for this first part is to identify these statements as something that is always true, something that is sometimes true, or never true. And these can be kind of tricky, so we'll look carefully at these. So here's a couple that are already worked out for us. So if there's exactly one plane that contains points A, B, and C, is that a statement that you would say is always true, sometimes true, or never true? Well, remember what we set up above. In a plane contains three non-collinear points. So if A, B, and C are in a line, if they are collinear, then we can have more than one plane. But if A, B, and C are not collinear, then we do have exactly one plane. So this statement is sometimes true. It's true if A, B, and C are non-collinear. So whenever we say that, it's always kind of good to be able to explain why you're saying that, to sort of justify your reasoning, kind of help you know that you're on the right track. So let's look at the next one. So we have points E and F are contained in exactly one line, and that was one of the first postulates that we looked at that said through any 2 points there exists exactly one line, right? And so that's exactly what that postulate says, so that's something we would say is always true. And then the third one, two lines intersect in two distinct points, M and N. That would never be true. That was the second to last postulate that we looked at. That was 2.6. 2.6 said if two lines intersect, their intersection is exactly 1 point, right? Never two distinct points. So that's something that is never true. So we're going to try 4 of those right here on our own. This is always a great time to pause and take a look. Try these on your own and see if you get them right, and then play the video to see if our answers are matching. So here we go. Number 1 says a line contains exactly 1 point, right? We know that's never true just by that very first postulate that we looked at that says a line always contains at least 2 points. So we know this would never be true. It's got to contain more than one. If it said at least 1 point, so that's when the wording of these can be a little tricky, and you really have to read carefully. So when they say exactly 1 point, that's our key word that allows us to say that this is never true, because it's never exactly 1 point, right? It's always more than that. So let's go on to the second one. Non-collinear points, R, S, and T, are contained in exactly one plane. So we know by one of our postulates up above, whenever we have 3 non-collinear points, we can always draw exactly one plane through those 3 points. So this is something that would always be true. Any 2 lines, L and M, intersect. So do 2 lines always intersect? Do they never intersect? Or maybe they do sometimes, but not always. So if I think of 2 lines, that we certainly know they can intersect. Like if you look at these 2 lines right here, they clearly intersect right at point B. So we certainly know they can. Is there ever a case where you have 2 lines that don't intersect? Well, look at these 2. So if this line is parallel to this line, right, we know that parallel lines don't intersect. And so there's a case where they can intersect, but they don't have to if they're parallel. So this is something that would be sometimes true. All right, and last one down here. So we got 2 planes, plane R and plane S. They intersect in point T. So what do we think about that one? Never true. right? That's not something that's ever true, because as we looked at the very last postulate that we talked about, 2.7, said that when two planes intersect, their intersection is a line, not a point. So that's something that would never be true. So we'll see a few of those in our homework today. Let me take you down to this next part. So in the next one, now they're going to give you a statement, and we have the diagram to go with it on the right. But now they're going to give us a statement, and we're going to decide which postulate matches the statement. Because when you identify the correct postulate, never, ever, ever just give the number of the postulate. Like, don't just say postulate 2.2, right? Because no one will remember what that means, right? Say what the postulate says itself. So don't just write the number of the postulate. And if you ever look up an answer in the book and that's what the book does, don't do that. Right? So when we do these, I want you to state what the postulate says, because I want you to understand what the postulate says. No, we're not trying to memorize postulate numbers. Those are going to be meaningless to you. So we want to know what the actual postulate says. So here's the description that we have going on. We got a couple segments going on, A, C, D, E. They're both in plane Q. And we talked about these in the last problem up here. We know that those two line segments are parallel to each other. That's what the little symbol right here means. It means that the two lines are parallel. So state the postulate that can be used to show the statement is true. Okay, and so this is where it's going to help you to go back to the list of the 7 postulates that we've identified already. So exactly one plane contains points F, B, and E. So if you look at point F, point B, and point E, those 3 points are obviously non-collinear. So which postulate matches that idea, right? And that would be, as you look back at your list of postulates, so here's what we would want to say. Through any 3 non-collinear points, there is exactly one plane. So you want to write this statement. Again, do not say postulate 2.2, because nobody will know what that means, right? I want you to actually write the idea, right? So you would write this full idea down for your answer. So through any 3 non-collinear points, there is exactly one plane. So that's what you would fill out for the notes for question 7. Let's take a look at number 8. And again, always good to pause the video, give this one a try on your own before I do it with you. So line BE lies in plane Q. So line BE, so again, even though there's not a line drawn in this picture, we still know with one of our postulates that if I ever have 2 points, there does exist a line through those 2 points. And we know that if 2 points lie in plane Q, then the line that I draw through those 2 points would also be in plane Q, right? So which one goes with that idea? So if we look back up here, if you look at 2.5, it says if 2 points lie in a plane, then the entire line containing those points is also in the plane. So, and that's the one that matches the idea that's going on right now. So this is the description that we would write. Again, don't put 2.5. No one will know what that means. You want to write the idea, the statement right here. So we would write this full statement for our answer on that one. And that's number 8. Let me take you to the second page. All right, here's where it gets fun. This is where we get our beginning of proofs. So the way that we are starting out with proofs is basically they want you to prove something in a very less formal fashion. So instead of going with a very strict 2-column proof, which is where we are headed, they're starting us out with something that's a little simpler by just saying, write it in your own words. So they call this a paragraph proof. A paragraph proof is where you're just sort of doing an informal explanation in your own words of how you know something is true. I wanted you to see something in your book that will help you lay out a paragraph proof. So if you go back to your book, and let me go to the next page. Give it a sec. It's moving a little slow. But if you go to the next page, what we're about to see is they sort of lay out the process for how you do a paragraph proof. And so this is a great model that you can help sort of go back to when you're doing your paragraph proofs, just to help you organize your thoughts a little bit on how you would lay this out. So let me go one more page. Sorry, it's just going super slow right now. I think it's because whenever we're on video, the computer runs a little slower. Okay, so let me scroll up. Even scrolling up takes a minute, so hold on. We'll get there. Okay, so here is the layout of the proof process. And let me point out some super important ideas. Step one is always, and this is going to be something that we talk about many times as we go through the rest of this chapter and chapter 3, is every single proof must start with the given information. So they will always give you some bit of information that they want you to start out with. All right, we call it the given. And so every proof must start in very step one with the given information. Now, this is always where we start. So we are going to list or restate the given information. That's always where a proof begins. And this is always where the proof ends. So a proof will always end with whatever it is that you're trying to prove. Okay, and so whenever you walk into a proof, they're going to give you two things. It's going to look like this. They're going to give you a piece of given information, and then they're going to tell you what they want you to prove. Right? And so whenever you do a proof, whether it's a paragraph proof or a 2-column proof or whatever, you will always start by restating the given information, and you will always end with whatever it is that you were trying to prove. Our goal is to figure out what goes in the middle, right? What information, geometry information, can we apply that will take us from the given information to whatever it is that we're trying to prove. So this is the tough part. This is where we have to come up with our own statements and our own reasons for getting from here to here. And this is when you're going to learn all these things called postulates and theorems and definitions, and we're going to use those three things in order to prove whatever it is we're trying to prove. So as we go through, when you start seeing things like postulates or theorems are just like postulates, but theorems you can actually prove. Postulates we don't have a proof for. It's just something that it is accepted to be true. But theorems you could actually prove. So whenever we see postulates or theorems or definitions, those are things that you super need to know. And we're going to come up with some handouts and things like that to help you keep track of all these postulates, theorems, and definitions that you need to know in order to do this middle part of the proof, right? And come up with these statements and reasons that are going to lead us into whatever it is that we're trying to prove, our conclusion. Here's one that I definitely want you to know, because you're going to see this one come up a lot, and it's something that we've already talked about. This is something that we addressed in chapter 1, and that is simply if you have a midpoint. So if M is the midpoint of segment AB, then that would tell us that this segment is equal or congruent to this segment, right? So if, and here's where all those if-then statements are going to come into play, but if M is the midpoint of segment AB, then what do we need to know is true? We need to know that AM is congruent to MB. So here's the way this will work in a proof. Whenever you see this information given to you, we then would say in the body of our proof, this idea. This is the conclusion that we would draw when they give us this information. So we talked about all those if-then statements in chapter 1. So here's the way this is going to work again is whenever they give you this, so the if is the conditional idea that they give you, the then is the conclusion that you draw based on this given information. So they would give you this, you will come up with this as your conclusion. right? So that's the way these things are going to play out within our proofs. So we're going to look at a couple ways that we can do this. And if you go back to your book, they give you some of these. So they give you an example of a paragraph proof right here. We're going to do some of those together, but you can always go back to your book to see some more examples like this one if you need some more examples. So again, the way this works is they're going to give you some information. We're going to start with that. They're going to tell you whatever it is that they want you to prove, and we are going to end with this. And our goal is, what can we fill out in the middle that will lead us from here to here? So let's go through some fun with paragraph proofs. All right, so here we go. So here's what they're giving us to start with. Remember, they're always going to give you some given information. So here's the given triangle ABC. You can see it over there on the right side. BD is an angle bisector. So this goes back to one of your definitions from chapter 1. So BD is an angle bisector of this angle right here. So you got to think back at what an angle bisector is and what information does that tell you. So what we're going to try to do is write a short paragraph proof to prove, so here it is what we're trying to prove, the angle ABD, that is right here, ABD, so that's this angle right here, is congruent to CBD, this one right here. So we're going to try to prove these two angles are congruent. This will be really short and simple because it's really just based on the definition of what this tells you. So this will be a nice short proof to prove. But remember, when you do a proof, you need to start with the given information and you need to end with whatever it is you're trying to prove. So here's their example. Because when you write this paragraph proof, you do want to base it on some kind of a postulate or a theorem or a definition that you can mention within the body of your proof, right? So you kind of want to say this. And kind of the nice thing about a paragraph proof is it's like in your own words. So it's like if I was going to explain this to a friend, here's how I would explain it in my own words. So it's not a formal proof, right? It's just something in your own words, but you still want to use geometry, ideas, definitions, theorems, right? Things like that from geometry. So we want to make sure that we're really giving a formal reason, at least, as to why we know this statement is true. So here we go. This is what they said. They said, so by definition of an angle bisector, right? So we learned in chapter 1. So you can look back at that definition, but we know that the definition says, well, then the angle was divided into two congruent angles. So if you look at angle ABC, the big one, the whole thing, when it is bisected, right, the definition of the word bisect means that it was cut into two equal angles, right? So since BD is an angle bisector, ABC, the whole angle, was divided into two congruent angles, right? Therefore, and we always end with this idea, therefore, angle ABD is congruent to angle CBD, right? So we started with the given information. We used a geometry line of reasoning in order to reason and to prove why this statement was true. Okay, and so that's how all these paragraph proofs should go. So make sure you start with this, end with this, and in the middle of that, you need to give some kind of a geometry reason as to why this is true. Let's try one here. So I have two here for us to practice on. So you can always at any point pause the video and try to do things on your own before I do, so you can see how you're doing. Look at this. This one's actually a little bit tough because it uses two ideas that I want to introduce you to right now. But I use this one, even though it's a little tougher, because it comes with two. I use this also as sort of a teaching moment here to explain two things that will be very common for us as we go down the line. So let me at least let's just talk about this first. So here's my given, right? This is my if. This is my then, right? So this is the given information that we need to start with. This is the conclusion that we need to end with. And we need to use some geometry reasons in between to get to this. So here's what we know. We know that A is congruent to D. We know that D is congruent to E. Therefore, here's what we are trying to prove. We're going to prove that angle A is congruent to angle E. So if you look at this, hopefully, logic would just sort of tell you, well, yeah, if A is congruent to D and D is congruent to E, then logically A would be congruent to E as well. And so we just need to use some kind of geometry line of reasoning to show why that's true. So we would start with our given information, that A is congruent to D and D is congruent to E. So we just always want to restate that. So you might say something along the lines of, since A is congruent to D and angle D is congruent to angle E, so since that is true, so we're going to restate the given. So what line of reasoning, if you were just talking to a friend, could you put into a paragraph that would tell you that this must be true? So here's where I wanted to show you two quick ideas before I finish this, so you can see where all this information is coming from. In the section we're in now, let me drop this down, sorry, it takes a second to transition. In your book, it explains something that we learned in chapter 1. Right? And in chapter 1, we talked about the idea of congruence. And the idea was that by definition of congruence, if two segments have the same, or if two angles, same thing, have the same measure, then they are also congruent. So in other words, if two segments, or if two angles are equal, then they are also congruent. And that's simply the definition of congruence. Right? And so pretty much we really think of things as being equal and things as being congruent as the same thing. And this is why we think of them as being the same thing. Right? That is the definition of congruence. So, in other words, let me go back to this. So, by definition of congruence, and I'm going to abbreviate here to keep things simpler, so I like to use a lot of symbols. By definition of congruence, I know that angle A is equal to angle D, and angle D is equal to angle E, right? Just by definition of congruence, right? That since they are congruent, they are also equal to each other. Okay, so there's our first idea. So now as I look at those, and I'm going to say, okay, well, if A is equal to D and D is equal to E, therefore, what are we going to be able to say about those two things, right? And let me show you where this comes from. There is a geometry property for this that I want you to, and I'm going to use some beautiful artwork to explain it to you. This is my beautiful artwork. So if I were to tell you that you are as tall as Tyler, and Tyler is as tall as Maddie, what would that tell you about your height compared to Maddie's height? Well, if you are 6 feet tall, and I said you're as tall as Tyler, and Tyler is 6 feet tall, and then I were to tell you that Tyler is as tall as Maddie, and Maddie is 6 feet tall, what would that have to mean about your height compared to Maddie's height? Well, if you're as tall as Tyler, and Tyler's as tall as Maddie, that would have to tell you your conclusion is that you are as tall as Maddie. And that's what we call the transitive property. So the transitive property says that if A equals B and B equals C, therefore our conclusion is that A would have to equal C. Right? And so that's the idea of the transitive property. So let me show you where that is, because this is something we'll be referring to in our next lesson. It's on page 136. On page 136, they're going to give you a few of these ideas. One of them is our transitive property. Transitive is very similar to substitution, right? Substitution is pretty much the same rule. Sorry, my computer's just running really slow right now. So transitive is kind of the same thing as substitution, with the idea that I just mentioned. If A equals B and B equals C. Well, if A equals B, that means I am allowed to substitute the value of A in for the value of B, right? And so I can take that next statement. All right, that's running really slow. Let me just go back to this so we can keep things moving. So substitution says that if this equals this, well, that means anywhere I see D, I can substitute this information. So it's the same as transitive. So if I put angle A right there, I'm allowed to do that because I'm subbing it in for angle D, right? So, and that's the same idea as transitive, is that idea of substitution. So we can say something along the lines of, by the transitive property, I know that angle A equals angle E. All right, by the transitive property. So why didn't we just do that from here? Why did we have to switch it to equals in order to say this? And now I got to switch it back to say that A is congruent to E. Let me just write it while I'm saying it. So angle A is congruent to angle E by definition of congruence. Remember, the definition said that if two things are equal, they are also congruent. So it goes both ways. If they're congruent, then they're equals. If they're equals, then they're congruent. That's just the definition of congruence. So we're going to put that in. So that means angle A is congruent to angle E. So we've gone on to prove that. So again, you guys notice that we started with the given information. We concluded with whatever it was we were trying to prove. And in the middle, we used a geometry property or two in order to get there, right? So we had to sort of support the path that led us to that conclusion. Guys, let me just tell you, not easy. So give them time. This is a process, right? This is a learning process for sure. The proofs, we're going to be dealing with these for the next chapter and a half, like I said, so give it time. These will take time. There's a lot of definitions you're going to learn. There's a lot of theorems and postulates and properties that you're going to learn, and this will take time, so give it time. Be patient with them, and we'll get a lot of practice on these. If you can handle one more here, let's do one more together. Okay, so yeah, like magic. I just changed the proof because I wanted to give you something a little different, and the one that they had was a pretty lengthy, complicated process. So let me take you through this one. So if you need to pause and write this one down real quick so you can do what we're about to do here. So again, we're given that M is the midpoint of BC, so think already about what that's going to tell you about this guy and this guy. We need to prove that 2 BMs equal BC. Right? So again, we would start with our given information. So since M is the midpoint of BC, since M is, and I'm abbreviating so I can shorten this a little bit. So since M is the midpoint of BC, so what geometry reasons can we now use to say something further? Right? Okay, so if M is the midpoint of BC, then what do we know? Therefore, we know that BM is congruent to MC. So therefore, BM is congruent to MC. And how do we know that? You always need a reason to back up your statement. So we talked about this earlier in the video, by definition of midpoint. Right? So, okay, so we now know that BM is congruent to MC. Right? That's what we just have shown so far. If they're congruent, what do we also know is true? Well, since BM is congruent to MC, then BM is also equal to MC by definition of congruence. We talked about that earlier in the video. Okay, so we now know that this is equal to this. What else do we know? So here's one of our huge ideas from last chapter called segment addition. Okay, so we know by segment addition, we know that BM plus MC is equal to BC. So big idea from chapter 1. So by segment addition, we know that BM plus MC is equal to BC by segment addition. So here's our statement and here's our reason. Right? We're always using some kind of geometry reason. Okay, so what do we got here? So if you look at this equation, since BM is equal to MC, can't we do a little substitution here? Since I know that MC is equal to BM, can't I substitute BM in for MC? So by substitution, I know that BM plus BM equals BC. So we are going to, because of this statement right here, I can now substitute in for MC. Since I know that MC is equal to BM, I can now sub in BM for MC. So by substitution, BM plus BM equals BC. So here's my reason, and here's my statement, right? So now let's conclude. So therefore, if I add those together, right, 1 BM plus 1 BM is 2 BM equals BC. And if we wanted to give a reason for that, we would just say something like by simplifying or by combining like terms. So you could say by combining like terms or by simplifying. So, and that would be our proof. So I'm trying to use a lot of common ones in here that you're going to run into a bunch, so you can see how they would get used. So that's going to be it for now for 2.5. But this is, again, there's more than one way to do this. Your wording might be different, and that's okay. For now, it's just about trying to get you to reason through the process of starting with this and ending with this by using geometry reasons in the middle, right? And so that's the goal of what we're trying to get through for this for now.